So how do we organize the stars? It's very important because they're so varied. And just like we have a periodic table of elements for the classification of elements, we kind of have a similar system, probably a little less complex, for the stars. So we're going to be able to plot all the stars, any star, whatever stage of its evolution, whatever kind of star it is, we can plot it on a diagram. And to understand how this works, let's start with how we might classify automobiles. So here's a graph of automobiles. And what you'll notice, it's a graph of horsepower as compared to weight. So the horsepower goes from low to high, while the weight, you might think it goes from light to heavy, but it's opposite. So the heavier is going toward the left, lighter to the right. That's how it is. And it'll make the analogy a lot better to the star chart we're going to look at shortly. So horsepower versus weight. Now normal cars are the vast majority. Most of the cars out on the street are normal, whatever that means. But they vary from heavy V8s to the light V4s, typically. So there's a large, fairly significant variety of normal cars. But then we have sports cars. Now what's different about sports cars? Well, they're up here in a different region of the graph. Notice they're at the higher horsepower level. And also they're not really heavy. They're more toward the light side, more toward the lighter side and the higher power side. Yeah, that makes sense. Racing cars are an extreme example of this. They're super powerful. That's the main feature, is the high power. To get that high power, you can't have it be too light because the engine itself is pretty heavy, but there's the racing cars at the upper echelon of power. Economy cars then, they're way down here. They tend to be more toward the light, but not necessarily, because maybe you need a great big bus, right? But the horsepower tends to be lower, so that's the economy cars. Well, so we're going to relate this to the stars, and horsepower will be brightness. That makes sense. For the stars, the horsepower will be the brightness. The weight is temperature. That's not quite as obvious, but you'll just have to go with it. So here it is. It's called the Hertzsprung-Russell diagram. And the first thing you'll notice is this diagram with the various categories looks similar to this one that we just discussed. So that's good. In fact, that's why it's done. Well, the main sequence stars, these stars here, are the normal stars. They are normal, where they actually, most of the stars are normal. And any given star lives most of its life in that normal main sequence arena. Turns out it's just where the stars are fusing hydrogen. So the normal ones vary from bright and hot, there's bright and hot over here, all the way down to cool and dim. So that's the same as with the cars on the road. Light and low powered to heavy and high horsepower. Okay. Giant stars, here they are. They're in a little separate category. Well, giant, they're more luminous. And they tend to be not so hot. They tend to be on the cooler side and fairly luminous. Then the supergiants, like the racing cars, the key feature is that they're super powerful. They are super bright. And notice this luminosity scale. This is compared to our sun. So it goes up by a factor of 10 with each increment. So the intensity, the luminosity, the brightness, the power of these stars is rising extremely rapidly. It's exponentially. It's an exponential scale here. So the supergiants are really, really very powerful bright stars. White dwarfs then, like the economy cars, they are low luminosity. That's one thing that's very obvious. And the brightness, the temperature varies across a significant spectrum. So temperature, as we've already discussed, the temperature is corresponding to color. So higher temperatures correspond to bluer, lower temperatures correspond to redder. So this is a good start, and let's investigate more characteristics of the Hertzsprung-Russell diagram. Well, now that we understand the basic idea of the HR diagram, the temperature and luminosity, let's look at another feature. Namely, we can get information about the radius. We can put the size of the star on here. And it's basically done as follows. So here we show a basic diagram. And what I'm going to do is draw a constant temperature line across here. So this red line is constant temperature. Notice the temperature is along the x-axis here, so it doesn't change. Well, what is changing? Well, it's the luminosity. If the temperature stays constant and the luminosity goes up, the only way to make that happen is to make the star bigger. So it goes bigger in that direction, smaller in this direction. So that's good. Well, what if we now do a constant luminosity line? Here's constant luminosity. What is changing here? Well, it's the temperature that's changing. For a constant luminosity, the star has got to get smaller as the temperature goes up. So here's the temperature is going up, but it's not getting any brighter. If you don't want it to get brighter, but you make it hotter, you better make the star smaller. Conversely, if the luminosity is constant and you're making it lower in temperature, you better make it bigger. So hopefully that makes sense. Those two situations are happening simultaneously. So we're going to combine the two ideas, and here we have constant radius. So the size is not changing. Notice the star gets more luminous as the temperature increases. So the diagram is about luminosity and temperature. If you have a constant radius and the luminosity goes up, the temperature has to go up. If you have a constant radius or size and the luminosity goes down, the temperature has to go down. And that's taken care of both simultaneously with this diagonal line going across here. So that's how we get these constant radius lines. Diagonal lines from the upper left to lower right for a given radius. And the larger radius lines, larger size stars, are going to be above smaller stars, which makes sense because the luminosity is going to be bigger for a given temperature. So these lines on this diagram in particular, we can put scales to them. And here's the one that passes through our star, the sun. So it's equal to the sun's radius. Underneath that, by a factor of 10, the sun's radius, 10 times less along here. So a 0.1 solar radius star would be along that line. Here it's 10 times the radius. Here it's 100 times. You can keep going. 1,000 times the radius of our sun. We are almost done with our understanding of this all-important HR diagram. Let's consider again, however, the classifications where we put stars on the diagram. We have the main sequence, and we have the giants and the supergiants and the dwarfs. But we can give more specific luminosity classifications to the various stars. And it relates to the region on the diagram where the star is placed. More related to the size, actually, rather than the luminosity, although they are all related. So we have the bright supergiants. So here we have the basic supergiant area, but broken down into class 1A, the bright supergiants. Then we have regular supergiants, class 1B, passing right through the biggest bubble on there. Followed by bright giants. So bright giants fall underneath that, class 2. Followed by the regular giants, class 3. So there's giants. Subgiants. So we have all these giant classifications. Followed by that, we have the most important one, which is the main sequence. Here it is. And to be complete, we'll go ahead and put in the white dwarfs. You could say it's not really even a classification because it's really a dead star. It's not an actual active burning star. But anyway, we'll call it class WD. So we can now specify a star based on its spectral classification, as we've already done, and also its luminosity class. As an example of that, we have our star, the sun. It's a class G25. What does that mean? Well, G2 is the spectral classification corresponding to the temperature, and the temperature here in color is also replicated up here with the spectral classification. So G2 is right about here. pass down here and go through the sun. And 5, the V corresponds to the luminosity class. It's a main sequence. It's possible that a star could be a G2 3, which would mean it's a giant, and we'd place it here on the diagram, or a 2 or 1b or 1a, etc. So that's how the luminosity classes work. It includes the spectral class, the subclass, and the luminosity class. And now we're going to look at, related to this, one more way to distinguish stars from their spectral lines relates to the luminosity class, as we'll see. The temperature of a star determines its spectral class. But how do you know? Given a certain temperature, therefore the spectral class, what luminosity class it's in? How do you know if it's a main sequence, a giant, a supergiant, a white dwarf? Well, here's how. It turns out that the width of the spectral lines for a given temperature, star, can reveal the luminosity class. And in a real clear picture here, we show the same spectral class star having the same absorption lines, supergiant, giant, main sequence. What do you notice different amongst these spectra? Well, what you notice is different widths of the absorption lines. Remember that the absorption lines are based on particular elements in the atmosphere of the star, causing absorption of photons of certain energies, which will remove those wavelengths from the light that's emitted from the photosphere of the star. So those are specific wavelengths, as we've talked about. Well, the spectra here corresponds to wavelengths. So you'll notice that on the main sequence, this is not just one wavelength, it's a small region of wavelengths, and that's the key thing. So there's different widths to these absorption lines. So the lines are not corresponding to exactly or precisely one wavelength. The reason for that is that big stars, like supergiants, actually have thinner atmospheres. And the thinner atmospheres means there's less energetic interactions amongst the atoms, or the particular ionized atoms. So there's less collisions taking place. Why does that matter? Well, because of the jostling, because of the collisions taking place amongst the atoms, that changes the energy profile so that the energy of the photon that's just right to produce one specific wavelength that's being absorbed, it's now a small range of wavelengths because of this energetic jostling of the atoms amongst themselves. So the really big stars, like a supergiant, which is just a star that's really blown up a lot, and as huge as it is, the atmosphere is thinner, and so the atoms are further apart from each other. They have less interaction with each other, less energetic jostling around, and so they only absorb those special, specific wavelengths corresponding to the electron energy transition. The smaller stars, like a main sequence star, has a denser atmosphere, so there's more jostling, and there's more change, a larger distribution of energies around that special electron transition energy that will allow for absorption. So you have broader absorption lines. Hopefully that made a little bit of sense. You know, it's a mindful, but here's an example. We have Rigel. It's a B8 star, 58,000 times the luminosity of the sun. This is a supergiant. And notice the relatively narrow absorption lines of hydrogen. A main sequence star of the same spectral class, B8, it's the same temperature. Look how wide those spectral lines are, because there's more energetic jostling of the atoms in the atmosphere, of the hydrogen atoms corresponding to those broader spectral lines. So that's how we can differentiate the various luminosity classes given a specific temperature of star.